To advance the technology of spaceflight is one of the great challenges of our times. Our Earth's immediate environment in space, the solar system, is the logical initial targets for such a technological advance. And space probes, such as Ranger 7, which took these pictures before crashing on the moon's surface, lead the way in space exploration. But another vital area of development in space technology is that of manned spaceflight, taking the human observer to the scene. In journeys to outer space and celestial bodies, there is no substitute for man, with his ability to evaluate what he finds there. An early goal of manned spaceflight is the scientific exploration of the moon, which requires landing men on the moon, then bringing them safely back to Earth. When our nation decided to achieve this goal by means of the Apollo program, several mission modes were studied. The mode selected is called Lunar Orbit Rendezvous. In addition to being the best way to accomplish manned lunar missions, it offers many opportunities for scientific research and experiments. This film is a description of an Apollo mission profile using the Lunar Orbit Rendezvous mode of getting man to the moon and back, and revealing some of the areas open for participation by scientists throughout the world. Rocket thrust is the basic capability we have had to develop for a manned lunar mission. This is a captive firing of the first stage of the three-stage Apollo Saturn V space vehicle. Here the engines of the second stage are shown during test. And this is a captive firing of the third stage engine. The complete space vehicle stands 36 stories high and weighs 3,000 tons. The first stage of the launch vehicle is powered by a cluster of 5 F-1 engines, which provide a total of 7.5 million pounds of thrust and burn 4,400,000 pounds of liquid oxygen and a kerosene blend called RP-1 propellant. The second stage of Saturn V contains 5 J-2 engines, yielding a total of 1 million pounds of thrust and burning 935,000 pounds of liquid oxygen and liquid hydrogen. The third stage of the launch vehicle uses a single J-2 engine with 200,000 pounds of thrust, burning 230,000 pounds of liquid oxygen and liquid hydrogen. The third stage can be ignited, cut off, and reignited. Above the third stage is the instrument unit containing navigation, guidance, control, and computer subsystems for launch and early flight phases of the mission. The launch escape system at the top of the Apollo spacecraft is shown during a test. It is a safety feature for saving the crew in case of emergency after they enter the command module on the launch pad and during initial phases of the flight. The 3 modules of the Apollo spacecraft are the command module, the service module, and the lunar excursion module called the LEM. The command module carries the 3 Apollo crew members on the round-trip journey between Earth and lunar orbit. It is equipped with subsystems for environmental control, communications, guidance and navigation, displays and controls, and landing on Earth. The command module has reaction control motors to control the spacecraft's orientation in pitch, yaw, and roll during reentry, and a heat shield containing special material which vaporizes to dissipate the extreme heat generated by reentry into the atmosphere. Below the command module and attached to it until just before reentry into the Earth's atmosphere is the service module. Its main propulsion system provides about 21,500 pounds of thrust used for mid-course maneuvers, changing course in space, slowing down to enter lunar orbit, and thrusting from lunar orbit into a return flight path. The service module also contains reaction control motors for orientation of the spacecraft in flight and carries the command and service module's main electrical power system of hydrogen-oxygen fuel cells, which provide pure water as a byproduct. The service module also contains an experiment bay for self-contained research instruments for use during flight in the space environment. At time of launch, an adapter encloses the service module's main engine and the Lunar Excursion Module, or LEM, which is positioned over the instrument unit structure above the third stage. In addition to facilities for 2 crew members and functional equipment and supplies, the LEM contains a descent engine, an ascent engine, a landing structure, and a cargo bay for equipment and experiments needed on the moon. Ground facilities and personnel essential to an Apollo mission should also be briefly described. These include facilities for final preparation and launch of the space vehicle in Florida and the Mission Control Center in Houston, Texas. Assembly and checkout of the space vehicle will be conducted in the Vehicle Assembly Building, shown here under construction at Launch Complex 39 at the Kennedy Space Center, Florida. Initial checkout of the first stage and integrated checkout of the completely assembled vehicle will take place in the high bay, which is 518 feet wide, 442 feet long, and 525 feet high. There are 4 checkout cells in the high bay structure. A mobile launcher provides physical support and facilities for test and checkout of the space vehicle from assembly at the Vehicle Assembly Building until liftoff at the launch pad. Its primary elements are the 2-level launcher base and the 380-foot tower. The mobile concept of launch preparations, that is, assembly and checkout of the space vehicle at a remote area, then depends on the prime mover, a crawler transporter which weighs 5.5 million pounds. At the launch pad area, final preparation for launching takes place. This includes loading propellants, installing explosive devices, final checkout, and countdown. Fueling operations are controlled remotely from the Launch Control Center more than 3 miles away. The Launch Control Center is adjacent to the Vehicle Assembly Building, connected by an access bridge. The overall command post for an Apollo mission is the Mission Control Center, located at the Manned Spacecraft Center southeast of Houston. Shown here is one of the 2 mission operation control rooms with complete displays at the control center. The center also has computer complexes, flight simulation facilities, and a communications center. To provide the communications and tracking required during a mission, a network of remote stations has been established around the world. Ships and aircraft are also needed to cover certain phases of a mission when the spacecraft is not within the range of land stations. Remote sites collect information and relay it to the Mission Control Center. If communications with the control center should be interrupted, remote sites will provide support to the spacecraft crew. Recovery operations will use aircraft and surface ships to provide dense coverage at pre-selected landing areas and a flexible mobile coverage of areas where landing might occur in case of early flight termination. The beginning of manned exploration of the moon will be the culmination of a decade of exhaustive research, development, manufacturing, and testing by as many as 300,000 men and women throughout the United States. Every material, every part, component, subsystem, and system will have been precisely designed and engineered, meticulously built and assembled, and will undergo exhaustive tests to ensure reliability before final preparation and verification tests are made on the eve of the mission itself. Hundreds of ground crew members directly participate in the mission and must be carefully selected and trained. Training of flight crews requires years. It includes academic classroom courses, briefings on every component and system of the spacecraft, extensive training on simulators, experience in simulated space and lunar surface environments, field trips for geologic studies, and research preparation in laboratories. The flight crew members available for Apollo lunar missions will include scientist astronauts selected primarily for their achievements in science. Part of their preparation is related to the selection of experiments and scientific inquiries to be carried out during a mission. An actual manned lunar landing mission can be said to begin when the Apollo Saturn V space vehicle and its mobile launcher are moved from the Vehicle Assembly Building to the launch pad. The 3 stages of the Saturn V launch vehicle have been checked out and assembled. When fueled, they command 8,700,000 pounds of thrust. Following a simulated flight test, the Flight Readiness Review Board has determined that Apollo Saturn V is ready for launch and turned control over to the operations organization. At T-minus 15 days, the mission director orders the move to the launch pad. T stands for the precise moment of launch. It must occur within an interval of time called the launch window, which depends upon several factors or constraints. For example, for the best visibility when the mission reaches the moon, the sun must be shining on the landing site at an angle between 15 to 45 degrees above the horizon. Due to the constantly changing relative positions of Earth, Moon, and Sun, the position of the Sun over any one landing site is right for only 3 days in any month. If alternate sites are available within the region of interest, this 3-day launch window can be increased up to 10 days. But the launch window is restricted even more. Range safety requires that the spacecraft be launched over uninhabited areas and in line of sight of tracking ships. So there is only a 26-degree sector through which the spacecraft can be launched. Since the Earth is constantly changing positions beneath the launched spacecraft, the inclination of the Earth at time of launch determines the Earth orbital plane which the spacecraft will enter. If launch occurs at the wrong time, this orbital plane will be such that injection from it will not lead to the moon. The correct Earth orbital plane will make possible a timely injection from it into the correct flight path to the moon within the limited time that can be spent in Earth orbit due to limited fuel and electrical power capacities of the third stage launch vehicle. Of course, the Earth also moves around the Sun at 67,000 miles per hour, and the moon circles the Earth at 2,300 miles per hour. All these factors reduce the launch window to a maximum of 4 hours for a daylight launch on any one day. Solar flares, meteoroid showers, and weather conditions also affect the time of launch. Moving the vehicle and the launcher to the launch pad takes 4 hours over some 18,000 feet of crawlerway. Later, the crawler transporter also delivers the mobile servicing structure to the pad. About 2 weeks before launch, deployment of tracking ships and remote recovery forces begins, and all ground support elements of the mission are equipped and manned. The Mission Control Center at Houston and the Launch Control Center at Cape Kennedy monitor and coordinate operations under the overall direction of the Mission Operations Director in the Office of Manned Spaceflight, Washington. The pre-flight phase on the launch pad consists of 15 days of pad and tracking network preparation, ending with a 24-hour terminal countdown before launch, which will be authorized only when every system proves to be in perfect readiness. Preparations include final verification tests, such as radio frequency tests, pressure and system tests of the giant fuel tanks, and final launch vehicle simulated flight test. This is one of the final steps, one last simulated flight on the ground before the real thing. Platforms and test equipment are then removed. The 24-hour terminal countdown begins after a thorough analysis of the simulated flight test reveals that all systems are go. Explosive devices are installed. Operational radio frequencies are tested. The mobile servicing structure is removed at T-minus 10 hours. After the LEM is closed out, the flight crew mans the command module. The module is then sealed. At T-minus 30 minutes, the launch escape system is armed. From this point on, the escape tower could be used for an emergency abort. When the mission director receives final readiness reports, he authorizes the mission to continue. At the Cape, the launch director starts the automatic launch sequencer. The ignition sequence requires 30 seconds, during which the umbilicals are released. The engines are ignited at T-minus 0, followed by release of the hold-down arms after proper engine operation is verified. The launch phase begins. The vehicle rises vertically for 12 seconds. It then begins a pitch-over maneuver. The first stage engines burn about 2.5 minutes, consuming all their fuel. During launch, voice contact is required between the crew and the Mission Control Center in case of deviations from the planned mission. An abort could be initiated automatically or by crew or ground officers. When velocity has reached more than 6,100 miles per hour, Apollo Saturn V is 45 miles downrange at an altitude of 34 miles, and first stage burnout occurs. The first stage is jettisoned. The second stage ignition follows a few seconds later. About 35 seconds later, the launch escape system is jettisoned. Hereafter, for safety purposes, the command and service modules could be separated from the space vehicle by the service module reaction control system and returned to Earth, or by using the third stage propulsion system, the mission could continue to Earth orbit, with the spacecraft then returning to a pre-selected landing area. The second stage engines burn for 6 minutes 35 seconds, thrusting the vehicle to more than 15,500 miles per hour, downrange 840 miles, and almost 100 miles above the Earth. At shutdown, the empty second stage is jettisoned. The third stage ignites for its first burn, which will last 2 minutes 50 seconds, and then cut off. This imparts enough velocity to bring the vehicle to the 17,454 miles per hour required for the nominal 100-mile-high Earth parking orbit, which the vehicle enters at T plus 11 minutes 40 seconds. During the boost phase, the launch vehicle computer and an inertial reference system in the instrument unit control guidance and sequencing. Ground personnel and flight crew monitor performance. The Earth parking orbit is entered at 1,400 miles downrange. Insertion is verified. That is, it is determined that the vehicle is in a safe orbit, capable of more than one orbit around the Earth. This is done both by the crew, by onboard navigation, and through radar tracking by the Mission Control Center. Normally, the vehicle will make 2 orbits before proceeding to the Moon. During this Earth orbit parking period, systems and crew biomedical checkouts are made, along with preparations to accelerate the spacecraft out of Earth orbit into a flight path to the Moon. Flight controllers on the ground, supported by system experts, analyze orbital flight performance, comparing system and guidance information from tracking stations and the space vehicle. The Ground Control Center then updates the onboard computer by feeding in corrected guidance data. Contingency planning provides that the flight crew be able to return to pre-selected landing areas, or ground control can order a substitute mission profile, such as continued Earth orbital flight and then a return to Earth. Injection into a flight path to the Moon must occur during the lunar transfer window, available for a limited time in each orbit around the Earth. In the normal mission, the mission director will make the decision to proceed to the Moon during the transfer window in the second orbit. To achieve the necessary velocity, the third stage is again ignited to burn for about 5 minutes. During the first 98% of the final third stage burn, the vehicle is not yet moving fast enough for its velocity to carry it to the point where the Moon's gravitational pull will overcome that of the Earth. Problems before such a velocity is achieved could result in a changed mission profile, which would rely on the Earth's gravity to return the vehicle in an elliptical flight path for reentry to a planned recovery area. When the third stage engine again shuts down, the vehicle is 163 miles above the Earth, traveling about 24,270 miles per hour on a flight path to the Moon. About 15 minutes after shutdown, ground control will make the decision whether or not to proceed with the repositioning of spacecraft modules. If the decision is go, the crew sets controls for coasting and prepares to initiate and control this next phase of the mission called transposition. The adapter panels shielding the LEM are blown open. The command and service modules are separated from the LEM by the service module reaction control system jets. Contingency planning for this critical phase includes use of the service module engine for return to a reentry orbit with the third stage and LEM abandoned. Normally, the third stage stabilizes the LEM, making docking possible. The third stage with the instrument unit is then jettisoned, and the spacecraft continues in its flight. From Earth to Moon will take about 3 days, depending on day of launch and lunar targeting. Since speed is gradually reduced by the Earth's gravity, then increased by the pull of the moon, the average velocity is 3,300 miles per hour. The crew monitors critical functions and systems, selects modes, adjusts controls, navigates, conducts scientific experiments, reports to the control center, and makes mid-course corrections. The spacecraft's orientation exposes its sides to the sun. It will roll slowly to distribute the heat. 3 mid-course corrections are scheduled to be made using the service module engine. The first, a few hours after leaving Earth orbit, adjusts the place and time of crossing that point where the moon's gravity exerts a greater effect than the Earth's gravity on the spacecraft's flight path. A second correction of the flight path may be made upon reaching this point called the lunar sphere of influence. A third mid-course correction may be made approximately 1 hour prior to lunar orbit insertion to ensure that the spacecraft will enter the correct parking orbit around the moon. The decision to attempt lunar orbit insertion is made before the line of sight with the spacecraft is lost by its going behind the moon. The flight path curves in as the spacecraft approaches the moon. Insertion into lunar orbit is made by firing the service module engine to reduce velocity. A 6-minute burn reduces speed almost 2,200 miles per hour. Sequencing and guidance control are automatic by the command module's guidance computer. Orbiting the moon about 80 miles above its surface, the 3-module spacecraft will cruise over the selected landing area before the LEM separates for its descent to the surface. The flight crew and mission control center confirm the accuracy of the lunar parking orbit and calculate and verify guidance parameters for the LEM's descent. 2 crew members then transfer to the LEM and conduct a complete checkout of LEM systems. The 3rd crewman will remain in the command module, which with the service module will continue in lunar parking orbit at a nominal velocity of 1 mile per second. The LEM is then separated. For it to get down within final landing range of the moon, the LEM's descent engine must be fired. The retro thrust reduces the LEM's velocity by 70 miles per hour, which puts it into a separate descent orbit. The descending LEM must coast through 180 degrees of arc to reach the point where its descent orbit comes closest to the moon. This means that the descent engine must be initially fired when the mission is behind the moon out of contact with the ground. If problems appear, the LEM's ascent engine can be used to return it to the command and service modules. In a normal mission, the LEM will coast about 1 hour until it reaches a point about 10 miles above the moon. In free flight, it would continue around the moon in an elliptical orbit. So the descent engine must again be fired to reduce speed and make landing possible. As the LEM falls toward the moon, guidance is all inertial and pre-planned. By controlling their spacecraft, the crew can check the landing area visually for the first time through the main LEM windows about 8 to 10 miles from the landing site and 10 to 15,000 feet above the moon's surface. This, on the first mission especially, is the moment of discovery, the moment of imminent completion and new beginning. The thrust of the descent engine can be modulated to permit the LEM to hover briefly above the lunar surface. If the crew observes an unexpected obstacle or abnormal slope, they can change course horizontally. By studying the surface as well as evaluating landing radar signals, they select the final touchdown spot. The control of the engine's thrust makes possible a gentle touchdown. Immediately after landing, the 2 men check the overall capabilities and condition of the LEM and report to the Mission Control Center and the orbiting command module. After the status reports, the men survey the moon's surface and prepare for exploration. The length of time they can stay on the moon will have been carefully pre-planned. Only 1 man at a time will be outside the LEM unless an emergency should occur. Portable life support systems will allow nominal 3-hour stays by either surface explorer. Exploration, gathering samples, and other tasks will have been programmed in order of priority during the planning for any mission. Instruments and experiments will be in place to be left behind for purposes such as studying the long-term effects of 1/6 gravity, hard vacuum, abrupt and extreme temperature changes, meteoroids, radiation, and the relatively constant airless environment of the moon. When it is time to return, a pre-launch checkout will be conducted as the LEM crew coordinates with the Mission Control Center and the command module. Initial conditions for ascending from the moon and rendezvousing with the orbiting command and service modules are inserted into the LEM's guidance system. The smaller ascent engine is used for launch, leaving the descent engine and the landing structure on the moon. The ascent engine burns for about 7 minutes, imparting a velocity of more than 1 mile per second. This rate of speed can be increased as much as 100 feet per second by the LEM's reaction control thrusters. Such performance flexibility allows changes in the ascent flight path and provides a small flexibility in lunar liftoff time, still using the direct descent mode to the command and service module's orbit. If the LEM must be launched from the moon's surface at any other time, it can be placed in a low parking orbit from which rendezvous can be completed later. Normally, the LEM's ascent orbit is elliptical, with its high point ideally coinciding with that of the command and service module's parking orbit. In a normal rendezvous, the change in the LEM's orbit is made when its trajectory reaches the command and service module's orbital path. The LEM's rendezvous maneuver begins approximately 5 miles from the command module. At this point, the LEM's reaction control thrusters regulate its velocity as necessary to complete the rendezvous. Alternately, the command and service modules could be maneuvered to pick up the LEM. Either vehicle has the capability of being the active vehicle in docking with the other. The lunar explorers transfer from the LEM to the command module. After docking and transfer are completed, the command and service module's condition and orbit are evaluated, and preparations are made to leave the lunar parking orbit and return to Earth. Prior to injection into the return flight path, the LEM is separated from the command and service modules and will be left orbiting the moon. The service module engine is fired while the spacecraft is behind the moon due to return targeting conditions. About 15 minutes later, the spacecraft is in the clear on its way home. Communications with Earth resume and the flight path is evaluated. The first mid-course correction, about 25 hours after injection, adjusts time of flight for correct reentry. A second mid-course correction may be made in another 25 hours, with a third correction scheduled for minor adjustments about 2 hours before reentry. About 20 minutes before reentering, the service module is jettisoned. The previously computed parameters for reentry are verified. The reentry corridor, only 400 miles wide and 30 miles deep, begins when the barely sensible atmosphere is reached by the command module about 80 miles above Earth. If the entry angle is too steep, the vehicle will enter too sharply and deceleration g-forces will exceed human tolerance. If the angle is too shallow, the vehicle will skip out of the atmosphere. The proper corridor lies between these extremes. Overshoot and undershoot will be avoided by rotating the spacecraft to change its lift capability, which to a lesser degree is like that of a glider aircraft. The spacecraft's ratio of lift to drag is about 1/3 due to its design and having its equipment located off-center to give it an offset center of gravity. Overshoot on reentry is avoided by rolling the spacecraft to reduce its lift, letting it fall toward Earth more steeply. Undershoot is avoided by rolling the spacecraft to increase its lift. The atmosphere forces it up and makes possible a more gradual descent. Re-entry can begin from 2,500 to 1,500 miles uprange from the touchdown point. Descent maneuvers can correct for small errors in re-entry timing and permit changing the landing site in the event of bad weather. Onboard guidance must be relied on during re-entry due to aerodynamic heating which ionizes the atmosphere, thus impairing communications with Earth. At 25,000 feet, the parachute housing cover is jettisoned and the drogue chutes are deployed. At 12,000 feet, the pilot chutes are deployed. 8 seconds later, the main chutes are fully deployed. They slow the descent of the spacecraft to a safe landing speed. Search and recovery operations in Apollo will be similar to those in the Mercury and Gemini programs, combining aircraft and surface ships for normal and contingency landing areas. From survey and evaluation on the moon's surface to analyses of specimens returned to Earth and continuing data from experiments left on the moon, new facts will be derived about the moon, the Earth, and the solar system. The Apollo program is enabling man to increase his knowledge of his environment in space. It will lead to further advances in the technology of space flight, and it may provide, by use of the moon itself, a unique research laboratory for the physical and life sciences.